Hello and welcome to 7.3 Hyperbolic Functions. So today we'll be looking at hyperbolic functions. These are functions that are formed by taking the combinations of two exponential functions, e to the x and e to the negative x. Okay, so we start off with the hyperbolic sign. You'll see all the hyperbolics have the h attached to the traditional trig name in it. So hyperbolic sine would be the sign with the h after it. Hyperbolic cosine would be the cosine with the h after it. Definition of the hyperbolic sine is e to the x minus e to the negative x all over 2. Hyperbolic cosine is equal to e to the x plus e to the negative x all over 2. Okay, we have some graphs for our 6 basic hyperbolic functions. You'll notice the hyperbolic sign kind of mimics like an x cubed, y equals x cubed type of a graph. Not exactly, but similar style. Hyperbolic cosine, the graph looks like a parabola. It's not a parabola, but it kind of looks like one. And the hyperbolic tangent, you'll notice it has this shape with horizontal asymptotes at y equals 1 and y equals negative 1. So if we look at our definitions of tangent, hyperbolic tangent is equal to hyperbolic sine over hyperbolic cosine. So similar to our regular trig function when we say tangent is equal to sine over cosine. Similar thing for hyperbolic cotangent. It would be the hyperbolic cosine over hyperbolic sine. And here we have the hyperbolic secant and the hyperbolic cosecant and their graphs. And you see how they're defined as well. Right? We have secant is equal to 1 over the hyperbolic cosine, and hyperbolic cosecant is equal to 1 over hyperbolic sine. Some other things, let's take a look at some identities. In this one we have hyperbolic cosine squared minus hyperbolic sine squared equals 1. That's probably our main identity. And we have other identities as well. This one comes up a lot. Hyperbolic sine of 2x is equal to 2 times the hyperbolic sine x times the hyperbolic cosine x. And then we have some other ones. Derivatives of the hyperbolic functions. So derivative of the hyperbolic sine is the hyperbolic cosine of u du dx. Hyperbolic derivative of hyperbolic cosine of u is equal to hyperbolic sine of u du dx, and it continues like this. Okay. Alright, so let's take a look at our first example. We're asked to find the derivative with respect to t of the hyperbolic tangent of square root of 1 plus t squared. Well, for starters, derivative of tangent is secant squared, right? So we would do hyperbolic secant squared of our argument. And then we would do derivative of the argument, so we have to multiply this times the derivative of square root of 1 plus t squared. So, yeah, I could say in general, this is 1 plus t squared to the 1/2. And if I take the derivative of that, I get 1/2 of 1 plus t squared. Drop the power, so that would be negative 1/2. And then I would that's it. And then I would say the chain rule tells me to take the derivative of the inside, and the derivative of 1 is 0, derivative of t squared is 2t. Okay, so now I could put this all together. I see that my 1/2 and my 2 would cancel. I would be left with a t, and then this piece would go in the bottom, right? So here's what I could do. I could have, I'll put this stuff in front. So I'll have t over the square root of 1 plus t squared, and then that would be times my hyperbolic secant squared of 1 plus t squared. And that would be the final answer. Okay. Let's take a look at our next example. Find the integral of hyperbolic cotangent of 5x dx. Okay. So the way we could write the hyperbolic cotangent is, we could say that this is the hyperbolic cosine of 5x over hyperbolic sine of 5x. So now we notice right away that we could have this as a ln situation, right? We do ln of the sine, and then the derivative of the sine would be the cosine, right? The only problem with that is when we do the derivative of sine to get cosine of 5x, then we have to multiply by 5 as well, and we don't have that, right? So if you're doing u substitution, you could say that u, let me do u equals sine, hyperbolic sine of 5x, du would be hyperbolic cosine of 5x times 5 dx. Okay, so we don't have that. That means we have to multiply by 1/5, right? So right now, as we're doing this, we have 1/5. I'll pull that out. And then we have u, and this will be du. Okay, so this looks just like our ln. So I'll integrate it, and I have 1/5 of ln of u plus c. So I have 1/5 ln of hyperbolic sine of 5x plus c. Okay, and that would be it. Let's take a look at another one. We have a definite integral this time of a square of a hyperbolic sine x dx. So we cannot integrate that, right? So what we need to do is change that to one of the identities that we could easily integrate. So let's refer back to, yes, so I'm going to integrate it. I'm going to use this identity here. Okay, the hyperbolic cosine of 2x minus 1 over 2. Okay, so I got my integral from 0 to 1 of hyperbolic cosine of 2x minus 1 over 2 . What I could do is, I have this over 2, I'm going to pull out the 1/2. Right, so I have 1/2 integral from 0 to 1 of hyperbolic cosine of 2x minus 1. And then this I could easily integrate. So I have 1/2. Now integral of cosine of 2x would be sine of 2x, but I would be expecting a 2, so to undo that, I have a 1/2 of sine 2x minus an integral of 1 is x. And then I'm going to go from 1 to 0. Okay, so now we just plug in the 1. So 1/2 of sine of times 1 minus 1. Okay, so when you evaluate this, you could plug this into a calculator. Should fix it with the hyperbolics. Plug into a calculator. Most calculators will have the hyperbolic sine functions in there. You'll notice that the hyperbolic sine of 0 is 0. Okay, so the second half here will be 0. In this first half we have hyperbolic sine of 2. So in here we have hyperbolic sine of 2, and then we have 1/2 of 1/2, so over 4, minus, and then 1/2 of 1 is 1/2. If you're doing this without a calculator, you could leave it at this step. If you plugged it into a calculator, you get a decimal approximation. It would approximate to about 0.40672. Okay, but if you're doing it without a calculator, this is perfectly fine. Alright, let's take a look at this next one. When we integrate, integrating from 0 to ln2. Now, one thing we could use to our advantage is the definition of the hyperbolic sine of x. Okay, we know what that is, so let's plug that in here. Right, hyperbolic sine of x is e to the x minus e to the negative x over 2. Okay, and we can distribute the 4e to the x into the parentheses, right? If it helps you, you want to pull out the 1/2 first, you could do that. That might make it a little easier to navigate. If you pull the 1/2 out, you multiply the 4 with the 1/2, right? Half of 4 was 2. So now you're just distributing 2e to the x into e to the x minus e to the negative x. Okay, so let's do that. Let's distribute. So 2e to the x times e to the x, that would be 2. Now e to the x times e to the x, that would be same base, so we add the exponent. So 2e to the 2x minus, and then 2e to the x times e to the negative x. We add the x to the negative x, that's a 0, so we get 2e to the 0. Okay, so we have 2e to the 2x, e to the 0 is 1. Okay, so now we're ready to integrate it. Okay, when we integrate 2e to 2x, that just becomes e to 2x, right? Because normally it's e to 2x, then we take the derivative of 2x, which is 2, which we have that anyway, so we have e to 2x. And then to be left with 2, that would be the derivative of 2x. Okay, and then we'll evaluate. So let's plug this in. We have e to the 2 ln2 minus 2 ln2 minus e to the 2 times 0 minus 2 times 0. Okay, well 2 times 0 is 0. E to the 0 is 1. So we have a minus 1 here. Now over here we have e to the 2 ln 2. Okay, well what does that mean? Well, another way to write that is you could have e, this 2 would go on as an exponent on this 2. So we have e to the ln of 2 squared. Now e to the ln of something, there's that old rule, when you have e to the ln of something, the e and the ln cancel. So all you're left with here is the 2 squared, which is 4. Minus 2 ln 2, and then here we have the minus 1. So you combine this 4 and the 1, so you have 3 minus 2 ln 2. And that would be your answer. If you do it on a calculator, you would just end up with 1.6137. Okay. Let's take a look at our inverse hyperbolic functions. So these are the inverse hyperbolic functions. So you have inverse hyperbolic sine, and you have all the other inverse hyperbolic functions. Just notice that in the top one here, the graphs are going to be symmetric about the line y equals x. Okay. Let's take a look at our next slide. The derivatives of our inverse hyperbolic functions. So these are the derivative formulas. And you'll notice there's a whole bunch of these, and there's a whole series of problems that go along with these as well. Okay. next. And of course, if we have the derivatives, that means we also have their integrals. So these are the integral formulas for those same hyperbolic, inverse hyperbolic trig functions. Okay, so let's do a problem. We have the integral of 2 dx over the square root of 3 plus 4x squared. It's a definite integral. Okay, so let's first try to tackle the indefinite integral. So pretend we don't have the limits of integration here. Can we match this up with any of these other forms? So we have a square root in the denominator, which some of these do, and we see a plus between the two arguments there. Let's see, it could be this first one. It could be this fifth one as well. Inverse of the hyperbolic cosecant. Alright, so let's take a look. Looks like it might be the first one. Let's see. So we got inside the square root. Well, the u is that major argument, right? That the u. So if our u here was, well, this could be u squared. So that means u could be 2x, right? Because 2x times 2x is 4x squared. That means if we have a du to that, du would be 2 dx, which we do have. That's good. Okay. And that means that a, that's like the coefficient or the constant. A would be, it would have to be this thing but the square root of it. So square root of 3. Okay, so it looks like we're getting somewhere then. So this is definitely in that form where we get the du up here, and then in the bottom we have a squared and then plus u squared inside a square root. Okay, so this is going to be equal to inverse of the hyperbolic sine of u over a plus c. Okay, so more specifically for us, this would be the inverse of the hyperbolic sine of 2x over square root of 3. Now this is for the indefinite integral, right? So now let's do the definite integral. So we got to plug in the 1 and the 0. So that means we have 2x over square root of 3, and we're plugging in 1 and 0. Okay, so that means we have here we plug in the 1, that's 2 times 1, which is 2, so 2 over square root of 3, minus, we plug in the 0, that would be 0 over square root of 3, which is 0. Now, inverse of the hyperbolic sine of 0 is just 0. And so all we're left with is inverse of the hyperbolic sine of 2 over the square root of 3. And you could leave that as it is. If you plug this into a calculator, if you plugged into a calculator, you would get 0.98665. Okay. Questions? Shoot me an email or bring it up during the lecture or the class. Have a good day. Have a good night. We'll see you soon.